right, let's get started. So we're still in the introduction. And today, what we're going to do is to overview this thing called Hadoop. Okay. What is Hadoop and why is it so useful? So in the previous lecture, we talked about the 3 V's of big data: volume, velocity, and variety. And as a matter of fact, the first two are especially problematic. The volume and the velocity. Imagine that we have a large chunk of data and the data grows at a really fast speed. Then, in terms of computing all the numbers and analyzing the data, it's going to be very much problematic. So for that scenario, there can be one possibility where we simply just purchase a larger computer, aka a supercomputer, perhaps. Another possibility is to add more computers and then make a distributed computing system. And in the context of big data, it is actually more beneficial to do the later than just going with a single computer, single large computer. So here's a comparison between local and a distributed computing. So, and this is crucial for understanding what Hadoop is for. So the local computing is a scenario where you have a single machine and the machine is capable of utilizing its own computational resources. And in case you have a supercomputer, for example, with a fast CPU processors and a large hard drive, then you should be able to deal with quite large size data sets. However, there's a limitation, obviously, right? There's a limitation in terms of how big and how fast a single computer can be. On the contrary, what happens in a distributed system is you can basically add, how many computational resources you want to add to a distributed cert. And in the distributed network, what can happen is, if a new data comes in, you can, store the data in one of those distributed computers. And then whenever it's necessary, you can load it up and then, process the data set. And even for the processing of the data set, you can distribute the computing tasks to multiple computers so that instead of one computer doing all the heavy lifting, you can have multiple computers taking its own part and do the computation more efficiently. So the scenario on the left is called a vertical scaling, meaning that, let me draw something. Okay. Vertical scaling, meaning that you're basically stacking up additional CPUs and additional hard drive to the same local machine. So it is doable, definitely, but in terms of the capacity, there's certainly a limitation, and it can actually be quite expensive. The other solution on the right-hand side is a horizontal scaling. So instead of investing your money on a single computing device, you can actually add just, more computing devices and then add it to the network. And then each individual computers doesn't necessarily have to be high-end computing machines. They can be just commodity hardware, like, personal computers on in your office or in your home. So there's nothing special to it. But when you have enoughly large number of computing devices connected to a network, you can start to leverage the power of numbers. And then you can start to leverage the distributed processing speed of multiple computers. And you can have the sum of the hard drive spaces of multiple computers, which as a whole can be quite large. So this is where Hadoop can come into play. Hadoop is an open source software platform for distributed computing and distributed storage systems. So when you have a very large data set, then you can host the large data set on a cluster of computers rather than just a single computer. And then you can process and analyze the data set by distributing the computing task across multiple computers. And Hadoop allows you to use a commodity hardware. And what I mean by that is the hardware, the computer you're adding to the Hadoop cluster, doesn't have to be a high-end computer. It can be just an old computer that's sitting in your office or sitting in your garage. You can just connect it up to a Hadoop server, and no matter how large or no matter how fast your computer is, it can contribute to the Hadoop cluster by adding more storage capacity and more computing capacity. So Hadoop, like I just said, doesn't require those machines to be high-end. So you can build a really fancy big data server from scratch by connecting up some commodity hardware, which is really the advantage of this Hadoop technology. Apparently, if you have a large number of high performance computers, that's even better, right? And that's what many big companies do, like Amazon AWS system, for example. They have a large number of high performance computers that are interconnected. But my point here is, even if you have computers that are not so fancy, you can still build a Hadoop cluster to do big data analytics. So as a matter of fact, Hadoop is not the first technology for distributed file system business. In fact, there was this thing called the Google file system, or GFS. And then Google actually published this white paper describing their technology that went into Google file system. And then in there, they also introduced this technology called MapReduce, which is basically a computing paradigm for distributed file systems. So that Google white paper was the foundation of all of these ideas behind Hadoop distributed file system. And when people first created Hadoop, instead of creating everything from scratch, they borrowed quite a bit of ideas from the Google file system white paper, because the white paper was open to public. So there was no restriction for them to quote unquote copy the technology described in the Google file system. And in fact, they didn't even bother to change the name when they developed Hadoop. So MapReduce, this thing is still the name that exists in the Hadoop ecosystem. So Hadoop started from an open source search engine project called Nutch, led by Yahoo. The guy named Doug Cutting and Tom White, those are the ones that drove this Hadoop project primarily. And on the side, the name Hadoop actually came from the name of Doug Cutting's kid's toy elephant. So he had a kid who owned a toy elephant, a stuffed elephant, and the name of that stuffed elephant was Hadoop. So that's why Doug Cutting named this file system after his kid's toy elephant. And then the logo of Hadoop is yellow elephant. Anyways, so Hadoop since then has been evolving from a really small set of software now into a large ecosystem that encompass almost entire suite of big data analytics and data management technologies. So it's actually really hard to keep track of everything in the Hadoop ecosystem, and especially for beginners, it's pretty complicated to understand all the technology in the ecosystem. So what you're seeing on the screen is actually a few subset of this huge Hadoop ecosystem, and there are many other technologies that I haven't displayed on this slide. In fact, the reason why I have chosen these technologies is because those are the necessary components that are that you must know in order to understand how Hadoop technology works. So with that being said, let's take a glance over each of this technology in the Hadoop ecosystem. So the first thing we want to know is Hadoop HDFS. So HDFS is a Hadoop distributed file system. So that's at the core of this entire Hadoop ecosystem. So what HDFS does is, this is, by the way, something that we're going to see in a few slides later. But what HDFS does is it's basically a Hadoop's version of a Google file system. And it distributes the big data across distributed servers so that a cluster of multiple computers can act like a gigantic file storage system. It is, quite simple to understand in some sense, because what it does is it's basically adding, more and more hard drives as, we connect more computers to the Hadoop server. But there's actually many more into it. So we're going to go through that in today's lecture. One thing I want to mention, though, is HDFS is a very reliable distributed storage system. So it not only distributes the file to multiple locations, it also creates duplicates of data so that if something happens in one of those Hadoop servers, then the entire HDFS can, still be up and running as a whole without any problem. So it is very resilient. It is very reliable. So that's why a lot of people are adapting Hadoop technology. Now, sitting on top of that is this thing called Yarn. So it's a funny name. So you'll actually notice that many names in the Hadoop ecosystem are quite funny, quite silly. Yarn stands for Yet Another Resource Negotiator. And what it does is basically, like the name indicates, it negotiates for computing resources in your Hadoop cluster. So it is basically a system that manages computing resources in your Hadoop cluster. It decides what gets executed and when it gets executed, manages which server nodes are available and so on and so forth. So in some sense, you can think of it as like a matchmaker or broker matching tasks with different computing resources in a Hadoop cluster. Now, sitting on top of that is this thing called a MapReduce. MapReduce is kind of a computational model or a computational paradigm or philosophy, if you will, which allows distribution of tasks across an HDFS cluster so that the things can be executed in parallel by multiple workers. So what happens here is MapReduce is not, like a program or a software. It's more like a computing methodology that basically splits a task into a multiple parallelly executable subtasks. Okay. And then send it over to Yarn. And what Yarn does is basically to allocate resources in the Hadoop data cluster, and then basically, do the matchmaking and allocate the computing resources to those MapReduce tasks. Okay. So the reason why it's called MapReduce is simply because there are mappers and reducers. So mappers, basically what they do is to transform your data and make it parallel. So what I mean by that is if you have a large chunk of data, what mapper does is basically to chop it up to smaller pieces. And then what mapper does in addition to that is to distribute that across servers or computing nodes so that these different chunks of data can be analyzed and processed across distributed computing resources. Now, after the distributed computing resources process the data and then generate some partial results, you will need to have a process to combine all of them and then produce a consolidated result, right? So that's the job of reducers. So basically, mappers are the ones that are chopping up the data task into multiple chunks, multiple smaller chunks, and reducers, on the other hand, are the ones that consolidate the results from those parallel executions of the code and produce a single unified output for your data analytics task. So we're going to talk about this Hadoop file system and Yarn and MapReduce much more in detail in a few slides later. So stay tuned. Now, these three blocks, which I color coded in yellow, are the core of Hadoop. And that's actually what Hadoop originally is. And then on top of that, the entire community has contributed to this Hadoop ecosystem because people find it it's pretty cool. Now, as a result of that, something called Pig was created, and the logo is quite self-explanatory, right? So sitting on top of all these technology, all these core Hadoop technology is a thing called Pig. And Pig is basically a high-level scripting interface for people who are not so familiar with computer programming. Okay, so what it does is basically it allows you to run all the MapReduce codes and all the functions of Hadoop and MapReduce without having to go through the hassle of writing and programming using Python or Java or those kind of like serious low-level languages. Okay. Instead, what Pig does is it gives you an ability to script some simple commands or simple queries, and then Pig converts those scripts into a MapReduce code so that it basically does all the job of computer programming for you so that you can easily analyze a large data set without having to learn computer programming. And the same level with Pig is Hive. And then Hive is pretty similar to Pig in a sense that it provides a high-level scripting language to access Hadoop and MapReduce. And in fact, what it does is it wraps Hadoop and MapReduce with this nice interface based on what is called SQL. So SQL is a database language that is quite easy to learn. And in fact, a lot of data scientists are already familiar with SQL because SQL has been around like forever. And then SQL is kind of a de facto standard for traditional relational databases. So you can safely assume that people who are familiar with database systems, they may already know what SQL is. So the idea behind Hive is to allow people to use Hadoop using SQL language. Now, we're going to talk about this as well in a later slide, but Hadoop and SQL, those are two different things. They are not actually compatible. SQL is what is called a relational data set, and then the whole architecture and schema is different from those of Hadoop. So making them compatible to each other. I mean, wrapping Hadoop with SQL is kind of a wild idea if you think about it. But Hive somehow managed to do that. So what happens with Hive is that you can script something using SQL language, and then Hive converts that SQL language into the code that can be executed by MapReduce and Hadoop. So it's a really useful tool, especially if you already know what SQL language is, and if you already know how to program using SQL. Now, on the very top, above everything else, is this thing called the Apache Mbari. So Mbari is a sort of an admin interface to kind of overlook the entire Hadoop cluster. So what it does is it gives you a graphical representation of the status of the Hadoop cluster, what kind of nodes are available currently, which node is down, and what kind of tasks are on the queue and wait to be run, and so on and so forth. So it is basically just like an admin view of the entire Hadoop cluster. So there's nothing really special about it. And in fact, in Apache Mbari, you can actually run, for example, Hive or Pig or even MapReduce through that Mbari interface. So I'm going to show you a little bit how it looked like later. But what Mbari basically is kind of a nice graphical user interface sitting at the really real high level so that you can kind of overlook the entire cluster and then interact with the technology without having to program a code. Okay. Now, that's kind of core backbone of the technology. Now what I'm going to explain is kind of a series of sort of a side technology that kind of enriches the Hadoop ecosystem. So the first thing I want to mention is what is called Apache Mesos. So Mesos is the reason why I put this right next to Yarn is because the function of Mesos is basically the same as Yarn. So Mesos is, simply speaking, a resource negotiator. It does the same thing as what Yarn does. So it manages computing resources across a Hadoop cluster. It schedules the task. It matches tasks with available computing resources and so on and so forth. Now, another technology I want to mention is this thing called Apache Spark. And then I kind of highlighted this with the orange color. The reason for that is this is going to be a core technology that we'll be using in this class. So Apache Spark is really exciting technology nowadays, demanded by a lot of employers. Spark is the hottest technology nowadays that is favored by a lot of IT companies, a lot of places. And as you can see over here, Spark is sitting at the same level with MapReduce. And what it does is basically it can interface with the Hadoop distributed file system, and then it can do basically what MapReduce can do, but with the faster speed and And in my opinion, it's more convenient than MapReduce while doing the same thing. The part of the reason why Spark is such a popular technology nowadays is that it can be actually 100 times faster than Hadoop MapReduce. So nowadays, a lot of people compare Hadoop versus Spark. And in fact, that comparison is actually wrong because you cannot compare the Hadoop core with Spark. I think the correct way to say it is Hadoop MapReduce versus Spark, because they're at the same level and they do essentially the same thing. And Spark is nowadays clearly a winner in this competition between MapReduce and Spark, because it's not only 100 times faster, but also it provides more functionalities that can be quite useful. For example, like what Pig and Hive could do, like what Hive could do, Spark also provides a SQL interface. Again, SQL is something that a lot of people already know if they're familiar with database systems. And therefore, the learning curve is much, right? It is much easier to learn for those people who already know SQL. So that's a clear advantage. On top of that, Spark also provides a real-time live streaming of data. So for example, let's say you're operating on a really popular online shopping mall, and then what happens over there is that data comes in and out like all the time in real time, and millions of transactions are recorded in a split second. So an ability to deal with that kind of large influx of data is going to be very, very important, right? Same thing with the social media platform and a lot of other IT platforms where the velocity is really high. So what Spark provides is a functionality to live stream data and then process the live stream of data in an efficient manner. So this is really powerful technology that can do many more things than what MapReduce can do alone. And then the use of Apache Spark is much simpler than the MapReduce itself. So it's a great technology, and it's certainly a valuable technology that you want to have in your resume, because that's demanded by a lot of companies and a lot of businesses. It can be very useful. The last thing I want to explain is this thing called Apache Storm. Apache Storm is primarily for live stream of data. So when you do like a real-time transaction analysis, real-time sensor analysis, those kind of thing, then what you want to use is Apache Storm. Okay, so the live streaming is supported by Apache Spark as well, but Apache Storm is more tuned toward live streaming of data. So it is more suitable for that kind of purposes. And as you can see, the level of Apache Storm is kind of across all three core technology of Hadoop. And what that means is, Apache Storm essentially has all the capacities of the Hadoop core system. So, for example, you can selectively decide whether you want to use the features of Storm itself or, going to rely on, for example, Yarn. So it is kind of a on its own, it's an ecosystem that contains a lot of different technologies. Regarding that, one thing I forgot to mention was that Spark can build upon either Yarn or Mesos for the resource negotiator. So Spark system can be designed in a way that is less dependent on Hadoop, and then make it instead rely on Apache Mesos, and then let it interact with the Hadoop distributed file system or something else. Okay. So nowadays, there are many other technologies for managing the distributed file system. So it doesn't necessarily have to sit on Hadoop, but this is kind of a standard way of implementing things in a lot of different places. Okay. I'm getting questions from the chat. Can someone install Spark on his personal computer? If so, how he can use cluster computing? Yes, that's a good question. So last time, in fact, I showed you some demo of how you could install your own, you could install Hadoop on your own local computer. So there is a way. And what happens is, if this is your local machine, what you're going to do is you're going to create a virtual computer within your local machine. So it's not a physical computer, but it is a virtual computer that exists in your local machine. And then within that virtual computer, you're going to install Hadoop. And as a result of that, you're going to have this like a sandbox where you can play with Hadoop without having to worry about, configuring the system, things like that. So it is quite, easy and convenient environment for people who want to learn Hadoop. And this is certainly doable. And when you do that, obviously, we cannot leverage the power of multiple computers because you have only one local computer. So it is just going to emulate the process, emulate the situation of having a Hadoop server. But what essentially happens behind the scene is you just have a single computer to do all the heavy lifting. So it's going to be quite slow, obviously, right? Because you're not leveraging the power of a distributed computing system. But it's certainly doable, and in that way, you can interact with, with all of this technology. In fact, so I'm gonna actually create a video explaining how you could install and download the Hadoop sandbox and then install it on your local machine. Now, the problem is, in my experience, it requires quite a bit of hard drive space. So what I remember is basically it requires like 50 gigabytes minimum. And in my experience, to be safe running this entire thing, you probably need 100 gigabytes of free hard drive space on your computer. And another thing is this virtual machine thing occupies a great deal of computing resource of your computer. So unless your computer is really powerful, like those gaming machines, you will have some struggles. I mean, I'm not saying it's impossible, but you will have some struggles in installing and running this virtual Hadoop server. So my recommendation is, okay, if you can afford, if you already have a good computer, then I definitely would recommend you to kind of, download the sandbox and then play with it. And, playing with Hadoop with your, by yourself is obviously better than, me explaining all the concepts without, letting you, having the hands-on experience, right? But in the meantime, it's actually not so much necessary to complete this course, because instead of relying on a Hadoop sandbox, what we're going to do is we're going to use this thing called the Google Colab. And then Google Colab sits on the Google computing farm, right? It's a Google Cloud, basically. And then what we're going to do is we're going to install Apache Spark in that Google Colab environment, okay? And like I said, by knowing how to use Apache Spark, you can indirectly manage all the tasks that can be done by Hadoop MapReduce, Yarn, and HDFS. And in fact, as a data scientist, you don't really need to worry about those technologies because, your goal is basically to be able to analyze a large chunk of data, as opposed to worry about all the minor little details in terms of nuts and bolts of big data systems. So unless you're a computer engineer who is interested in all those database technology, which is, by the way, not the scope of this class, you don't really need to know all this core technology in use. Rather, I would recommend you to stick with Apache Spark because this is basically like an interface to all of this. Okay, so my point here is, if you don't have a good computer, that's perfectly fine. I'm not going to require you to, purchase a new laptop or, things like that. So don't use this course as an excuse to tell your parent that, oh, I need a good computer because this dumb course called the Big Data Analytics, the professor told me to buy a new computer. No, don't do that. Okay. Instead, we're going to use this Google Colab, which only requires a web browser. Okay, and your computer doesn't have to be a good computer. And then we're going to see how you can use this Apache Spark technology on Google Colab so that without purchasing a good computer, you can still learn all the necessary technology that is relevant for data analytics. Okay, so the reason I spent some time emphasizing this is because that's actually the question that I'm keep getting from last week. So I wanted to clarify that you don't actually need to install everything on your computer. You just need a web browser. So essentially, the fair comparison is, Spark versus Hadoop MapReduce. You cannot compare it with the entire Hadoop, core technologies. What I mean by interfacing with Hadoop technology is not that Spark can replace the entire thing. Okay. Spark can only replace Hadoop MapReduce, but by knowing Spark, you don't have to really do all the, manage all the nuts and bolts of HDFS, for example, because Spark installation is going to sit on top of either Yarn or Mesos, and then they're going to, be sitting on top of Hadoop distributed file system. So what you need to do is you basically need to put in commands in Apache Spark, and then let this guy to handle all the things that's happening behind the scene. So just to clarify, okay? Other questions? Perfect. So let's move on. Now, that was a really broad overview of Hadoop ecosystem. And obviously, you don't have to memorize all that, but I still kind of recommend you to remember what these core technology do, okay? So even if you forget about everything, I still want you to remember what MapReduce is and what Yarn is, what HDFS is, and what the Apache Spark is, at least. Okay. Of course, the better is to memorize, all of this, because this is already a kind of a short list of Hadoop ecosystem, and there are many other relevant technologies in the Hadoop ecosystem, like Uzi, Zookeeper, Taz, all funny names. But at least these four technologies, Hadoop, MapReduce, Yarn, HDFS, and Spark, I want you guys to memorize what they essentially do and what they are useful for. There is certainly an overlap. That's a good question. There is certainly an overlap regarding the live streaming capacity, but they are quite different, in fact. The overlap is only that live streaming part, but Apache Storm has actually a lot more to it. Apache Storm is more specialized in live streaming data processing, whereas Spark is more on the machine learning, distributed computing, those kind of things. So they're not exactly the same. And the reason why Hadoop has a bit of learning curve is, in fact, because of that very reason. A lot of beginners have hard time understanding the difference between the technology, because in fact there are lots of overlaps. Like, for example, in this ecosystem, there are two different things that does exactly the same thing, right? Mesos versus Yarn. And a lot of other technologies that I skipped, they actually do the same thing as well. There are lots of overlaps. And the reason why we have so many overlaps is because the Hadoop ecosystem is not the creation of a single company or a single initiative. It's an open source project, which means anyone who wants to contribute to the Hadoop ecosystem, they have full freedom to create their own module and then submit it. And then once it gets accepted, then it becomes a member of the Hadoop ecosystem. So yeah, as a result of that, the hierarchy is actually a lot more complicated than this. I probably have overly simplified by drawing this picture, but this is to understand. This is to help you understand what it really is. But for example, Spark doesn't have to be sitting on top of Hadoop, because Spark can be an independent thing which can utilize different distributed file systems than HDFS. So for now, let's not worry too much about it, because if I start to talk about those things, it's going to take forever, and then you're going to be just more confused. So for now, like I said, let's just focus on those four technologies: Spark, Hadoop, Spark, MapReduce, Yarn, and HDFS. And as far as you know roughly what they are, you should be fine. All right. So that was a really broad overview of the Hadoop ecosystem, and let's see what HDFS essentially does. So I'm basically talking about those core Hadoop technologies: HDFS, MapReduce, and Yarn. The yellow boxes in the previous slide, and we're going to talk about this real world situation. So let's say we have a project manager, Trisha, and she is managing a team of 4 people. We have John, Sanjay, Sarah, Bob. And what Trisha does is to assign projects to each of those team members. Okay. And as she assigned the task to each of the team member, Trisha takes a note. Okay. I just assigned project A to John, I assigned project B to Sarah, project C is assigned to Sanjay, project D is assigned to Bob. So Trisha, as a project manager, keeps a record of the work distribution, okay? And we're gonna call that a metadata, okay? Now, consider this hypothetical scenario. Let's say Bob is sick, okay? Or let's say, let's consider a more extreme scenario. This poor guy has gotten into a car accident, okay? And then he cannot be at work for the next several weeks, okay? Now, so far, everything was just working smoothly and everything was fine, but all of a sudden, this guy got into an accident, and then Project D is in trouble. So in order to resolve this issue, our project manager, Trisha, goes to, say, John, and say, hey, John, how's it going? You've been doing great recently. Keep it up. And John is like, yeah, great. Thanks. What's going on? Because all of a sudden, Trisha, pretends she's really friendly and so on. And so John smells something fishy. Okay. So Trisha says, well, John, so Bob, had a car accident last night, and he won't be able to work on Project D for a while. Can you actually take care of Project D on behalf of Bob? And now John thinks, yeah, that's it. I knew there was something fishy, right? And then says, well, Trisha, sorry to hear about the accident of Bob. but I guess I have already so many things that I have to do with Project A, and I don't think I have a bandwidth to work on Project D on top of Project A. Maybe why don't you ask Sarah or Sanjay? They seem to be much more flexible. Now, Trisha is as a diplomatic person, what she does is she says, you know, John, you've been doing great so far, and then you've been the most, productive employee in our team. So, I know it's going to be an additional work for you to take care of Project D, but I'm convinced that you're going to do a great job in managing Project D on top of Project A. And, it's not going to be like a permanent thing. I mean, the moment that Bob comes back to work, I promise you that, Bob is still going to be in charge of Project D. So this is going to be just a backup project for a couple weeks. But instead, you will still get credits for, both Project A and Project D in your annual review. So, you're going to get some pay raise, perhaps. Now, after that conversation, John thinks that it's actually a great deal, right? So he decided to accept Project D as a backup project. Now, with that good news, what Trisha does is to assign Project D as a backup project to John and then update the metadata accordingly. And in the meantime, she learned the lesson. She learned the fact that if I just distribute the project, one-on-one to each person, then if something happens, then we're going to be in trouble. So what Trisha does now is to distribute the project, the primary project, to each individual. But in the meantime, she also assigned the backup project. So that each employee is involved in more than one project, one as a primary and then the other as a backup, so that if something happens, the other employees can still back up the project and then let the project running without a problem. So what you just saw here is essentially what Hadoop distributed file system does. Okay. So I'm going to replace all the faces with computers. And that's exactly what happens in Hadoop cluster. And this is called a master-slave architecture. So the master node is basically our project manager, Trisha. And then the slave nodes are basically the workers that does the actual work. So what master node does is to manage the metadata, the ledger or the note that records which task was assigned to which slave node, okay? So let's say similar to Bob's situation, a computer goes down. Now the computer caught on fire, or somebody tripped over the power plug. So for whatever reason, let's say the slave node slave node 4 is now unavailable. In that case, the entire Hadoop cluster as a whole is going to still be able to run up and running without any problem, because they already have some backup projects, backup tasks assigned to each of the slave nodes. So this thing is called fault tolerance. This is a very important concept associated with the Hadoop distributed file system. What fault tolerance says is, even if there's a problem in one of the nodes or some of the nodes, the entire cluster will still be up and running without a problem, because there are backups. Okay, so that's a key notion that differentiates Hadoop from many other technology, many other database technology. So now let me try to compare this with those usual SQL databases. So again, I'm using this word a lot, SQL. So SQL is short, it stands for Structured Query Language. So SQL is actually quite convenient scripting language that many data analysts prefer to use. They're actually very simple. So the language looks like something like select all from table 2. It's something like that. The language itself, looks pretty similar to the English language. So many people without computer programming background can easily pick up SQL language. Anyway, so SQL is, not only a language, but also kind of a standard of, standard for database systems. Okay. So the main difference between SQL and Hadoop is that Hadoop is schema on read, and then SQL is called the schema on write. And what it essentially means is that, let's say when we have a, let me erase my drawings. Let's assume that there's a SQL database. Okay. And I'm going to call it A. And then here's another SQL database, B. Okay. And let's say we want to move the database A to the database B. Okay. And then perhaps merge them together. Now, in order to do that in a SQL database, we need to know the exact structure of database A and the exact structure of database B. And not only that, we need to ensure that the structure of database A is compatible with the structure of database B. Okay. And what I say by structure or schema is basically how the values are organized. So, in this picture, we have lots of different veggies. And those veggies are categorized into different bins, right? So they're sorted nicely into different bins so that when there's new sets of veggie coming in, then what happens is we need to sort those veggies according to their types, right? And then put those veggies into the bins that correspond to, right? Correspond to what's in there already. So now instead of consider them as vegetables, let's consider them as numbers, okay? And in the SQL database, you need to have some definition of how those numbers should be organized, okay? Now, on the contrary, what happens in a Hadoop system, aka schema on read, is that you don't really have to have that kind of structure. You can just put all kinds of different veggies into one bowl and then just have them sit there. Now, when you have a database A and database B in Hadoop, and let's say you want to merge database A to database B, what you need to do is essentially, think of database A as a salad bowl, and then database B as another salad bowl, And what you essentially do is to pour the contents of the salad bowl A to the bowl B. And that's it. You don't have to have a worry about, comparing the elements to elements. Does it make sense? The reason why the SQL database can be sometimes problematic is because, let's say, in the database B, let's say we have red onions. Okay. And then there's a database A that I want to merge into database B. But in this case of database A, we have just onions, yellow onions, right? So they are kind of compatible, but not quite, not exactly. So that's where the dilemmas start to begin, right? Should we merge onions with red onions? Are we going to allow that or not, right? So all of them has to be manually defined. And then the database A, the set of vegetables A, needs to be transformed and then re-represented in a way that is compatible to the database B. So to help you understanding this a little more, here's another graphical illustration of what's going on. So essentially what you're seeing on the right-hand side are the salad bowls, okay? So think of them as veggies. And in order to define this, what you need to have is you need to have some, logical relations between the bowls, okay? So for example, if you're gonna call a variable student ID, then the same thing should still be called student ID in many other other salad bowls, right? So you need to have some sort of a structure like this, and then the structures need to have the relation between different data table in case where there's more than one data table. And by enforcing this kind of structure, SQL can maintain the ordering of a database system. Whereas in Hadoop, interestingly, what happens is a new data come in, and what HDFS does is to just compress the data and then distribute the data to multiple data nodes. So what it does is essentially to compress the file and then make a copy of that file to multiple locations. And while doing that, it doesn't really worry anything about ordering and structuring of the data. It just compresses the file as is without worrying anything about the structure, and then it just makes a copy everywhere. So this sounds like a chaos, right? Especially in contrast to the SQL databases, where there's the strict order and everything. But that's actually the real power of HDFS, because it doesn't really bother you to, add more data and then, and then the compatibility between the data and so on and so forth. It just lets you add more and more data to the database without having to worry about all the rules and, things like that. So let me go back a few slides, sorry. The reason why I call this schema on read and schema on write is because of that reason. So schema means, again, structuring or ordering of a data, and then you have to enforce that before writing any new data to a database. Versus schema on read means we're not going to enforce any structuring. We're not going to do the gatekeeping. We're going to just welcome everyone to come into our Hadoop database. Okay? But instead, when I need to search for something, then that's when I'm going to that's where I'm going to impose a schema okay, as opposed to imposing the schema at the time of writing. So we're going to just keep it as a salad bowl, or we're going to just keep it as a giant jumble of a lot of different information. And when, let's say, we are looking for tomatoes, then we're going to go to the database and then try to sort out tomatoes and then retrieve that to the user. Okay. So it doesn't awful sound like a, efficient way of computing things. Because if you have a good ordering at the beginning, then you don't have to worry about retrieving the information. You can just pick a tray, or, pick this bin, and then just, throw it to the user. And that's it. You don't have to like search through this giant mixture of different things. So obviously the SQL sounds a lot more efficient than Hadoop. But that's actually not the issue, because Hadoop is going to leverage a distributed computing system anyways. So the search process is actually not that terribly difficult. Because imagine now, instead of one person searching in the bowl of salad, we're going to distribute this, we're going to break this down into smaller chunk and then distribute it to 100 different people. And each individual among those 100 people, what they need to do is they need to just search it, within their portion. So one person picking up all the tomatoes in a salad bowl sounds like torture. But if you distribute that, then, well, it becomes a pretty simple task. So that's the true power of Hadoop distributed file system. Okay. Now, going back to this, like I just said, Hadoop basically just makes a copy of the same file and then store that in a different data nodes, different slave nodes, and then keep it as is. Now, imagine a social media platform. Consider, say, Facebook. Okay. And let's say we have 1,000 servers connected via Hadoop. Okay. So when you upload a photograph, when you upload, when you post something, all of those information goes into the Hadoop server as some compressed file format. So you basically just zip it, and then you're going to create a copy of your photos and posts, musics, and everything across those 1,000 servers. Now, let's say we decided to replicate the same file, say 20 times. Okay. So what that means is it's going to create 20 different 20 copies that are identical to each other, but distributed across the file system. Okay. Now, the reason for replicating data is, like I said earlier, is because of fault tolerance. That's one reason. But if the purpose of making copies is just fault tolerance, do we really need to create like 20 copies of it? Right? Because what are the chances where a server catches a fire, or get completely disconnected, or whatever? So would it be sufficient to have like maybe 3 replications, right? That sounds already enough. Fault tolerance is one reason, but that doesn't really justify why we need to create 20 copies, for example. Okay. Well, in fact, there's actually many more than just the fault tolerance. Okay. Let's consider this example. So again, we're still comparing Hadoop versus SQL. Okay. Let's say, again, the Facebook example. All of your photographs, posts, musics, and everything, in case of Hadoop, it is distributed across multiple servers, and then you have replicated copies. In SQL, what happens is maybe we have a master metadata node, and then the data is basically stored in different. I mean, you can still make SQL in a distributed file system. So in a very simple, perhaps overly simplified example, you can have a computer that has all the photos and posts, everything that was published in January. You can have another computer that holds everything published in February. You can have a computer that has everything about March. You can have a computer that has everything published in April, and so on and so forth. Okay, so let's, for simplicity of the discussion, let's assume that that's the way we're storing the data. Now, what happens, for example, let's say a search query comes in. I want to see all the pictures of Steve Beck. Okay, that was a search query. Now, what happens here is that search query goes to the master node, and then what happens is it sends out the search query to the distributed file system. And so far, so good. Okay. Now, imagine that there was a problem. Okay. So one of the nodes, for some reason, was not working or was not returning the result to the master server. So in case of SQL, what it does is it waits forever until it receives the information from the March server. Okay. And then after a certain period of time, if it still doesn't receive anything from the March server, then it's going to return error to the user. So that's a SQL relational search procedure. On the other hand, what happens in Hadoop is that the search query comes in, and the search query is then converted to a computer code. And that's why we start to apply schema. Okay. And then that is distributed to multiple distributed computers that contains the relevant copy of information that that contains the information, that contains a file that are relevant to the search query. And what happens here is multiple servers are going to do their portion of work. Okay. So, we talk about briefly about MapReduce. The mapper over here is going to split the search query into different tasks. So mapper is going to perhaps say, hey, you're going to search for all the pictures in January. And hey, you're going to search for all the pictures in February. And you're going to search for all the pictures in March. You're going to search for all the pictures in April. So mapper basically assigns that task. Okay. And then let the distributed computers to search through all the information. And then after each of the nodes does its own, small chunk of task, then the reducer is going to combine that result and then return it to the user. Now, during this process, interesting thing about Hadoop is that it doesn't like to wait. Instead, the moment it receives the data, it spits out to the user. Okay. So even if one of the computers catches a fire, it still is going to return the result to the user. On the other hand, like I said, in case of SQL, it's not going to return the result if there is a problem in one of the servers. So for SQL, it's called a two-phase commit, because you enforce the consistency and the structure and the ordering at all time, from the beginning, from the writing of the information and to the accessing of the information. So the entire life cycle, from the creation of data to the access of data, throughout the entire life cycle, there's a gatekeeping process. Versus Hadoop doesn't really care. It just returns whatever is currently available. So the reason why I'm comparing this is because as a data scientist, you need to understand, which option is more preferable than the other. And I'm not saying, Hadoop is superior than SQL or vice versa. Neither approach is right or wrong or superior or inferior. But you have to decide in the context of big data. So in many cases, big data, Hadoop is obviously preferable approach because this is more resilient, fault tolerant, and there are so many benefits to it. But the downside of that is that Hadoop doesn't enforce the integrity of data. So there's a good chance you're missing something, especially in case some of the servers goes down and so on and so forth. You're not going to get a consistent result. Each time you run a search query, the Hadoop server is going to return different result. Whereas in SQL, you are guaranteed to receive the same result all the time if the search query is the same. Okay? So, but in case of big data, people really don't worry about the consistency because the cost, the effort to keep the consistency is too high in case you have a large volume of data or large velocity of data. So instead, people are like, yeah, forget about it. Let's just, make it not fail too frequently. Because in case of SQL databases, since they're enforcing the rules too strictly, you often come across the situation where your search query fails and, that's a headache. So Hadoop is, I guess, a little more loosened database system, which is tolerant of faults and mistakes, whereas SQL is more strict. So generally speaking, Hadoop is preferable for big data, but obviously there are exceptions. For example, even if the data size is large, even if the velocity is large, there are some applications where you need SQL database. A good example of that is a financial transactions of your bank or other financial institutions. We're talking about a valuable information. We're talking about the information of money. So you don't want a situation where each time you query your bank balance, right? The balance of your bank account. You don't want a situation where you're getting some inconsistent responses from the database, right? At one point, you send a search query and it says you have $500 in your bank account, and the other day you search for it and then it says you have only $200, and you're going to be like, what the heck, right? So in those cases, SQL is obviously be a better approach, and in that case, you have to give up some of the benefits of Hadoop at a cost of consistency. But again, in a lot of scenarios, Hadoop is obviously a better solution and preferable solution. So that's it for today. And we're going to be continuing. We're going to continue to talk about Hadoop and HDFS in the next lecture. And then hopefully after that, we're going to talk about Spark, and then I'll show you some of the examples and how things actually run on computers and things like that. So thank you so much, and I'll see you guys on Thursday.